logics. How do I full screen this? Okay. Today's the last lecture. The last lecture is the first 6 weeks of the MSDS cybersecurity class I taught last year. They didn't know how computers work, you do, so that means we can run at 12x speed. Okay. We're going to go over threats and threat models, trace properties, crib key structures, linear temporal logic, Bougie automata, including DFAs and safety and liveness, and then I'm going to talk briefly on the CIA triad, and then I will dismiss you and you will have learned all of the things that I expect you to learn this term. Security is incomplete as a concept, and conceptually, when students come to me about cybersecurity, we often have to get back to the idea of what we even mean by security. I like to ask these 3 leading questions. What is secure? From whom is the what of the secure? And for whom is the what of the what secure? So when we're securing something, we are essentially deciding winners or losers or distributing privilege. And we are also attaching attributes to some entity or object or class or something like that. So there's no such thing as a secure computer in the classical sense. There's a computer that is secure for some application for some population, right? Bitcoins are secure in some way. Specifically, the ownership of a Bitcoin is secure. For the senders and receivers of Bitcoins, or the spenders, the transactors, ownership is secured. And anyone participating in Bitcoin is secured against double spending. So the coins themselves are secure from abuse. Well, we don't have to necessarily think of it as abuse, right? So when I think of security in the context of Bitcoin, it makes a lot of sense. Now, because you know what Bitcoin is, you're able to understand this, and so we save a lot of theoretical work, and that's how we can get through this content more expeditiously. Now, whenever we're thinking in the context of security, we should always be thinking about limitations. Most things that are later presented as security flaws or issues or breaches or so on actually come from something happening that was allowed but should not have been allowed. And so with Bitcoin, the most common and the most expected case is always that a third party can tell who uses the service. So we don't know how many Bitcoins you have or what you got them for, but we do know that you have Bitcoins. The most likely way to know this is to detect IP traffic from your device to a Bitcoin node, right? A third party can tell when the Bitcoins are being sent. So if a bunch of Bitcoins move around, for example, at the same time as an insider trading scandal or something, this is sufficient to raise suspicion. And perhaps, and I think this one is much harder, a third party can tell the amount of the transaction. Because so many transactions happen at the same time, right? A lot of this stuff gets mixed together. Oh, that was so sad. That's very sweet. Okay. So maybe there is a sufficiently large amount of Bitcoins moving that it itself is suspicious. And I think this is true with US dollars as well. I think if you start transmitting over like 5,000 US dollars over a wire to another country, it is inherently considered suspicious no matter what you're doing. Unless, of course, you're a faceless, evil multinational corporation, then it is assumed you're acting in the interest of the United States government, right? Now, we're going to solve this problem with the technique of threat modeling. Threat modeling is something that's been around for a while. I really associate it with OWASP, which is maybe like the web and application security is probably the WAS. Maybe the O is open. Maybe the P is like Professor Calvin. I'm not sure what it stands for. If you just look at the p.org, that's a porg, which is a character from Star Wars Episode 8, right? Any Star Wars appreciators? Porgs? Yes. Why are you... No, I'm correct. Don't shake your head at me. Yeah, no, Cass is behind you judging me. You're not a Star Wars appreciator? Are you Trekkie?
Also, I mean, I don't know. It's good.
Do you like the Alien films?
What?
Do you like the Alien films? Okay, cool. All right. You get a pass. Cool. All right. Okay. So a threat model usually comes with 5 bullet points. A description of the subject to be modeled. That's usually the what of being secured. Assumptions that can be checked or challenged. So, for example, you generally speaking assume some finite amount of compute power, right? Potential threats to the system. That's me, right? Actions that can be taken to mitigate each threat, and that's usually things like 496T, SHA, RSA, things of that nature. And a way of validating the models or threats. So I have pointed out before this class that I did not make you write any proofs this term, and that's because I'm a nice, good, chill professor that doesn't teach hard classes, right? But I could have made you write a proof of everything we do. And for example, I could have made you write a proof of the bounds of the probability of a hash collision between 2 SHA hashes, right? And you can think about how you would write that proof, and it would be non-trivial, but it would be interesting to do, right? So somehow we have to validate that. It's not always with proofs. I break this down into what, for whom, from whom, any limitations, and So we can think of these things formally or informally. Usually when I say formally, I mean formally in the standards of like a professional society. I don't mean formally in the terms of a formal science like mathematics or philosophy or even linguistics, right? So we can apply this method to Bitcoin, our most beloved blockchain. So what is it? It is a currency. It is a decentralized cryptocurrency, right? But fundamentally, it is a currency. And the decentralized and crypto actually come from other bullet points on here. Who is it for? So the client of Bitcoin is an economy with internet access, right? So I do think of the clients of the US dollars being like the world economy, right? I don't think necessarily we are the people that use and benefit from US dollars. I could probably get by with the barter system. I have a lot of really cool .python scripts that I could probably trade for mochas every day, right? So we actually have to have a full comprehensive economy large enough that it can't rely on the barter system, right? Because those are the entities that require use of currency. From what? Or from whom, perhaps more properly, but from what here also works as well for Bitcoin. Bitcoin is secure from a central authority. There is no central authority in Bitcoin. Bitcoin is difficult but not impossible to attack from a central authority. And it's difficult but not impossible to attack if you are a surveillance entity or even a surveillance state. And it is, it's actually relatively easy to perform fraud on people that use Bitcoin, but it's actually very difficult to defraud the system itself, right? So as ever, the weak point is the humans, right? Are there any limitations to Bitcoin? Of course, the public ledger. A lot of people that are super into privacy don't like the public ledger, and there is no amount of proofs or, in the case of the Bitcoin paper, there's not actually a proof there. There's just a rhetorical argument using probabilities that is simulation-based and therefore unrigorous. That there will not be too much information leaked about people using the public ledger, right? Generally speaking, this was not considered persuasive at the time. People got over it when they saw how unbelievably cool Bitcoin was, and they just use it because it's cool. But in fact, the public ledger is a major limitation, and a lot of people don't like that. But the entire thing doesn't work without a public ledger. The public ledger is the alternative to the central authority, so you either get a public ledger or a central authority, right? So when we're building a threat model, we can often proceed in 4 steps, right? So we've got a lot of things going on. We have which questions we're asking, and then we also have how we actually build this thing, right? It has been impressed upon me by people in the application security space who, generally speaking, have different degrees than I do. They will often have, for example, an IT certification or something like that. They might be in a business unit, something of this nature. Anyways, everyone loves diagrams. Raise your hand if you love diagrams. I see every single hand went up. That's incredible. Unanimous decision. Yeah, everyone loves diagrams. And why do we love diagrams? Because we get to write code that makes diagrams and we love writing code, right? So that was very straightforward. Okay, so we're going to make a diagram. We're going to identify threats to the sort of system we've sketched out. And we're probably going to identify these visually or graphically. Similarly, we're going to identify mitigations. And then when we have completed this diagram step, because diagrams are not necessarily rigorous, we're going to take some validation steps. We're going to make some assessment of whether we have actually solved the problem we've claimed to solve and whether we have actually fulfilled the service agreements, so we're actually providing the services that we claim to provide. So here's an example. This is a diagram. This is lifted directly from Satoshi Nakamoto. This is a Bitcoin. This is not the blockchain. This is a chain of ownership, right? The chain of ownership here is, oh, that looks conspicuously like a linked list, right? Maybe I should teach a class on Bitcoin and also teach linked lists at the same time and see if anyone notices. I bet no one will notice. We also have signatures here, right? So we have a private key used to generate a signature. We're hashing things into a signature and so on. So this is the diagram of the system. Now, does this admit any forms of attack? Well, the most obvious thing that jumps out to me here is it seems like if anyone gains access to a private key, then this whole thing is insecure. Of course, that's always true, right? Oh, look, it's the Bitcoin transaction visual.svg. Ooh. Always hyperlink your graphics, students. Okay. So what if 2 entities have the same private key? What is the probability of that? Well, we were using 496-bit private keys, which means that the probability of a collision is, well, between 2 of them, it's 1 in 2 to the 496, and then there's some like birthday paradox thing, so there's some sort of combinatorial proof as more and more entities use it. I don't actually know any probability. That's not true. I don't want to think about probability right now. So you could probably come to some conclusion over how likely you are to have hash collisions based on some number of users. But 2 to the 4096 is a very large number. I don't know that I could count that high before the end of class. So I'm not going to attempt to do that. What happens if dishonest nodes have more compute power? This is actually robust to that. This is not protected by compute power, right? There's no proof of work in an individual transaction chain. So the thing that would have to happen in that case is some form of forgery, right? Which is still protected by the same collision. What happens if the internet goes down? Absolutely nothing. This is probably written on a hard drive or perhaps an inferior solid state drive. Can I get some loud boos for solid state drives? Yeah, we love rotating magnetic media here in this classroom, right? And so if the internet goes down, this is going to persist in data storage somewhere, and so you don't have to worry about too much about losing that. Oh, I'm behind. Okay, so keys are 496-bit. Okay, we've talked about that already. Okay, so how do we validate things? I have not talked too much about validation of the security goals I've described in this class. For example, I showed you how to make a RSA signature, and I did not persuade you that it was invulnerable to attack. I simply persuaded you, hopefully, that it was possible. So we're going to look at digital signature here, and we're going to look at it in the context of an attack game, which is the methodology used by the crypto book, which is the partner book for this class. I don't know how many of you are reading it. Probably none of you, because I don't know, it's not how I would write things, but that's okay. So we're going to use the idea of a chosen message attack. What is a chosen message attack? That is when someone other than me wants to convince the world that I said something. So someone else picks a message and encrypts it as if I signed it. So we're going to use an existential forgery. And what this is that some attacker can output a message signature pair. What is the message signature? The message is the ciphertext. What is the signature? The signature is the hash of the unencrypted text, right? That's how we made our hash signatures. So if someone can create a combination of the ciphertext and the hash digest, then that person should be able to persuasively pass off some message as if I wrote it, right? And this is bad. So this is the form of attack that can happen on a signature. Someone passing themselves off as me. It's an impersonation attack, right? So how do we deal with that? Well, we're going to think of signature protocols as being this tuple of functions. They are generate, sign, and verify. And they exist over the messages, which are M, and the signatures, which are big sigma. We're going to get into a variety of different mathematical notation today, and there's some things I should let you know of. These slides today are irregularly in either LaTeX or HTML. That's because I ran out of time to translate everything to the same language, and I have source documents in different languages. They're also from different textbooks, so not all of the conventions are maintained the same, right? So I'm used to using S to refer to sets. Here it's being used as a signature scheme. This is an ordered triple over functions, right? Sigma is almost always used the same way. Sigma is a collection of letters in an alphabet. In this case, the alphabet is the bits, right? So we have a collection of bits of some length. This is also continuing our practice from earlier this term of considering messages to be M, and we just have a big M here, so the little m's are elements of big M. This is the set of all possible messages. This is the set of all possible hashes, right? We denote our adversary A, and we're going to do something called an attack game. So someone is going to attempt to attack the signature and create the forgery. So how does this work? The challenger, or the attacker, or the adversary, is going to generate a key, and a key is a tuple here. So that's the private signing key and the public verifying key. We just called these the private and public key. You don't have to use RSA, but you're welcome to do so. You're allowed to use ECDSA if you know what that is. So what do? We're going to generate these keys, and we're going to distribute our private signing key to the attacker, okay? Now, the attacker, or sorry, I should say adversary. The adversary is going to query several times. So what does this mean? I'm going to make a series of requests. I'm going to say, hey, can you sign this thing? Hey, can you sign this thing? Hey, can you sign this thing? As that happens, I am going to attempt to learn patterns about how the digital signatures are performed. So, for example, one of the first things I will probably learn is the size of the digital signature. Yes.
The challenger is the program generating the keys.
Yeah, the challenger is the key generating. Yeah. So the adversary is going to query the challenger. Why? Because that's who's trying to gain access to the system, right? And so I am attacking the entity from whom I am attempting to make a forgery. Okay. I'm going to challenge some number of times, and I'm going to see some number of combinations of ciphertexts and hashes, when these are the things we called in big M and big sigma, okay? Then, once we have given some number of small m's, so those are signed messages, my mouse, we are going to attempt to make some forgery. So how are we going to do this? Well, we're going to create a little sigma. Why is it little sigma? Okay, because it's part of big sigma. So this is a signature. This is a speculative signature of our chosen message. We're going to attempt to sign this, and we're going to attempt to generate a forgery. We're going to give this forgery to the adversary, okay? Now, at some point in time, the adversary will gain enough information about the private key of the entity which it is attacking that it can successfully, or at high probability, output a candidate forgery pair. The candidate forgery pair is the chosen message with the likely satisfying signature. And this is part of, it's part of the Cartesian product. Can I hear it for Cartesian products? Who loves Rene Descartes? Any relation? No, we don't love Rene Descartes. French, right? Yeah, I also don't like philosophy majors. Okay. Wait, no, are you saying you're a philosophy major?
Philosophy major. Descartes sucks. His ideas were bad.
Sounds like me. Okay, so, and also Pope Francis. That's two people that are just like that. And now I'm sad because I'm thinking about Pope Francis. Okay. Pope Francis compared me to a nuclear weapon once. Okay, we say that the adversary wins the game if the following two conditions hold. Yes, and compared, yeah. Yes, we love gender. That's not true. Do not put there, I love gender. Okay. Anyways, the attacker wins if at high probability you successfully create a forgery. This is a way to think of an attack and a validation. Okay. I've been told that when I teach people about threat models, I should go over these 5 techniques. You're supposed to define the scope and depth of analysis. What was the scope and depth there? We kept this very abstract, right? We lived only in bit space. It is noteworthy we lived only in bit space because we did not make any considerations of metadata, and we did not make strong considerations of how many people would be seeing these messages, for example. So commonly, in the case of a chosen message attack, what you actually do is you just watch web traffic coming from some node and you see a bunch of signed payloads coming out of it. And you just look at all those signed payloads, and then that is how you attempt to come to some conclusions about the methodology of the signature. We did use a visual understanding. It seemed like visual understandings didn't pull that well in this class. That's good. That means you're starting to become smart. We visually modeled the attack possibilities. We identified the threats. What are the threats? Someone attempting to pass off a message that I did not sign as if I signed it, right? And how did we document this? Well, we said the real problem you have to look out for basically is that someone sees some large number of messages that you sign and comes to some conclusion about your signing technique, right? Easy peasy. I would not go so far as to say lemon squeezy, but I would think about it, right? I had for breakfast, I had a strawberry lemonade electrolyte powder. It was delicious. Okay. In terms of scope, big business major wants me to talk about the term stakeholders. So you're supposed to think about who uses a service. In the case of Bitcoin, this is criminals, right? Who provides the service? In the case of Bitcoin, that is the same criminals. Who benefits from the service? In the case of Bitcoin, that is still the same criminals. And who does not benefit from the service? Everyone else. And specifically, the entity that does not benefit from the service is anyone that wants to breathe clean air or drink clean water. Because Bitcoin is an environmental disaster, right? But we still love Bitcoin. Why? Because it's mathematically interesting, right? So I guess I also benefit from the service because I got to teach this class. And you got to benefit, well, okay, you can decide if you benefited from it or not, right? Let's see those course evals for us. I am not going to give you time for course evals today. I have to talk very quickly for a long time. Okay, when it comes to scope, who can answer these questions? So I think it matters a lot who answers the question of who Bitcoin serves, because my impression is big crypto is of the opinion they could spend enough money to buy elections in the United States and like purchase legitimacy through that way. I don't think that's true. I don't think you can spend enough money to convince people that your fake money for criminals is real, but we'll find out, right? This also matters a lot when it comes to something like enterprise security. So who gets access to healthcare data, for example, because I probably don't necessarily agree with the government on who that is. There's been sort of a large amount of data coming out of, for example, the Social Security Administration lately, going to people that I don't think should have it personally. But the people that made that decision, they thought they should have that data, right? So when we think about who the stakeholders are, there's not generally going to be widespread agreement among who the stakeholders are, and this is a contested site of power. Now, I thought I should get a PDE certification for this class because I talk about power, difference, equity, and diversity, depending on what the D stands for at any given day. And this is really where the PDE comes in. Bitcoin essentially privileges people that currently have Bitcoin, right? That's kind of weird. It is inherently conservative, is inherently biased towards the status quo. It is often advertised as a disruptive technology, and it is impossible for it to be a disruptive technology because it only gives power to people that already have power, right? Here's some code. This is my visual representation of the blockchain. We all love the blockchain. Do you all remember looking at this and thinking how cool it was? That's what I thought. Okay, so the threats. What if someone changes a spend amount or a receiver or attempts to double spend back to themselves in a previous block? And what if someone loses their private key? These are all bad things. I expect this one. I don't think you can change things without cooking the hash, which means I love cooked hash. Why did I say that? Now I'm hungry. I had some delicious cauliflower tacos for lunch instead of going to the modern geometry final projects. So this should be rejected by any blockchain node. If they see a change to a transaction, that should not be permitted because it doesn't hash properly, which means every blockchain node is responsible for hashing things, right? What happens if G submits a second spend? Well, then this should be a double spend. This should be detected by comparing G against how many Bitcoins G can spend, which means it is incumbent upon every Bitcoin node to check and make sure no double spending is occurring by consulting the public ledger, right? So these things are both posing computational costs to your system, right? What happens if G loses their private key? Haha, tough luck. Okay. I have documented this as follows. I wrote the Bitcoin paper. I am actually Satoshi Nakamoto. I didn't want you to find out this way either. And then I also wrote Bitcoin Core. My GitHub username is, let's see, probably one of these. I am Habasto. Okay. Who loves traffic lights? No, because automobiles are bad. Okay, we don't love traffic lights. We love traffic lights only because they are a state machine, right? So I'm going to use a traffic light. I'm going to diagram, identify threats, mitigate, and validate. We're going to carry traffic light through the remaining 120 slides. Oh my gosh. Okay. All right. Trace properties. I think of security in terms of properties. A property is something that can be formally specified, and it is a description of a system. These security policies are distinct from the what of the threat model. The what is the system we are discussing. Security policies are properties of the system we are discussing. So it is the how. For example, a security policy could have the property of being secure, okay? So I think of properties in a very specific way. I think of them as trace properties. Did any of you notice that when our guest speaker came in, the guest speaker discussed trace properties?
Yes.
Exactly, right? So I bamboozled a guest speaker into agreeing with me. Even though, by the way, that talk was about machine learning, right? Yeah, I noticed it was about machine learning. I was like, hey, do you have anyone that can give us a talk on crypto? And they're like, yeah, sure. I was like, this is machine learning. Anyways, it also contained trace properties. Someday I may be begrudgingly forced to admit that maybe machine learning is academically interesting, but no one's gotten me yet. Okay. A trace is a sequence of states through which a system passes over time. Okay, what does this mean? I'm running a computer program. The sequence of states through which the system passes over time are the values on the stack and the heap. That's what it means. The states are the state of program memory. Program memory is contained in its totality in the stack and the heap. So a sequence is an ordered collection of the descriptions of the stack and the heap. A state is an atomic point in time at which there is some values on the stack and the heap. The system is the entity that is populating the stack and heap with certain values. And all of this is happening over time. I'm going to do everything chronologically or temporally or however you want to think of it. I'm not going to use real time. I find real time interesting and it's a bit out of scope right now. So we're going to think of traffic lights. In what state may a traffic light be? Someone say one state a traffic light can be in. Did someone say orange?
I said
Oregon? I like where your head's at. Okay.
green arrow.
Green! Okay, great example. Okay, so I'm not going to do turn signals because then it would make all of my graphics more complicated, but of course you can fit them in, right? In what sequence may the different states of a traffic light occur? Good question, we'll go over that. Does a traffic light implement a security policy? I think so. Do traffic lights change over time? No. Time isn't real. Okay. Well, unless you're an electron, in which case you go forward and backwards. Yeah, okay. We model a traffic light as a state machine. A state machine is a mathematical model of computation. It is an abstract machine that can be in exactly one of a finite number of states at a given time. These are often called SSMs for finite state machines. Why are they finite? Because I don't have a hot new startup selling infinite states, right? Even though my mind can be in infinite states, it can only be geographically in a finite number of states. Though I do think it can be in a number of states higher than one, because I don't think that territorial claims have to be mutually exclusive, right? That's my impression. Okay, so we can denote the state of a traffic light by the lit color, and everyone in the class at once said, repeat after me, wow, this class is lit. Wow, I can't believe you fell for that. Okay. Should we all point and laugh? Okay, that'd be mean. Yeah, fair enough. Okay, thank you, Ben. Okay, that was Ben, right? Yeah, okay. So make sure, like, be cool and never seem desperate is my recommendation. Okay, cool. All right. So here is an example of a lit trace. We got RGY, RGY, RGY. Hell yeah. Okay. Let's review some traces and see if they are from a traffic light system that is operating properly. Also, you can specify this however you want. So here is a summarized lambda that you can apply to get RGY or DY. Okay. Does starting state matter? This is mandatory participation.
Yes.
No. Okay. So I roll up to a traffic light, right? And it's yellow. That doesn't tell me that it's functioning improperly, right? Now, if it's blello, then we have a problem, right? Yeah.
The question was unclear. You say, does that matter? Well, yeah, starting state will do something.
Fair enough. I'll give you full credit. Okay. Does the ending state matter? The terminating state. For the security property. That's a great question. Okay. All right. Does the length matter?
Yeah.
I'm going to say no to that one too. Okay. Does the number of unique states matter?
Yeah.
Okay. I think you're all wrong. I think only order matters. Because, let me make this claim. We want to determine if a traffic light is violating a security property. I think the security property a traffic light can violate is it can have a hard or fast transition from green to red, which causes cars to not be able to stop in time, which causes intersection collisions. Wow, that was really hard to say. But like a car accident, right? Now, if I'm observing a traffic light and I see that the traffic light is currently in some color, it does not matter which color it is in. The only thing that I can do to infer that there is some security violation is I have to see I have to see a green to red transition, right? So only the order of the states matters. Now, I do think unique states matters because if I see a blello light, then I know that the traffic light is functioning improperly, right? If I see an Oregon light, I know the light is functioning improperly, right? So when I am thinking of how I determine the security property of some trace, I do not commonly necessarily care about the number of unique entries in the trace, right? And that is my claim I'm making. And I also think I sometimes, but not always, care about the initial starting state. Now, if I am modeling a C language executable, it does matter what the starting state is, because if I start with stuff on the stack and in the heap, that could affect my performance, right? It is specifically, I believe, the case with a traffic light that if I observe it in the state of yellow, green, or red, initially, that is not sufficient to determine whether it is functioning properly or improperly as a safety property. I cut about 20 slides before that, so that's why that might have been unclear. Okay, can I get some vague head rattling that I'm talking sense? Really? Okay, all right. Can I get some negative feedback? Yes. Blello is the color between blue and yellow.
When did blue come into the
It's not valid.
Yeah, because you violate the security properties. Yeah, if I were like coming up to an intersection, there were a blue right, like people would flip out and do weird stuff. Oh, is that just a green light? Oh, so Blello is fine? Okay, so Blello's allowed? Wait, are we doing additive or subtractive primary? Yeah. What's your real question?
Traces when we define a security problem on the trace property as improper jumping in one. How do we construct that trace property? How do we understand that is on a program with a more complicated, because red, green, yellow, red, green, fuck. Whatever it is for the traffic light is very simple and predictable. For any kind of complex problem, it seems like a user input and you get a trace that you couldn't really predict. So,
Yep, it's hard.
oh,
Okay. It's actually provably intractable. But that doesn't mean we can't try really hard. Okay. We're going to say a system satisfies a property P if all possible traces produced by a system are in the property. What do I mean in the property? Well, in the property is a set of traces. So if I have a system that's producing traces, all of those traces form some set. If that set is a subset of the property, then the system satisfies the property. This may be an infinite number of traces, or include traces of infinite length. This is important. I was using finite state machines. I'm not supposed to do things infinitely. Computers are allowed to do things infinitely. We now have the theoretical frameworks to allow that to happen. So this happens with a persistent web server, right? It never has to terminate. Systems may satisfy more than one property. For example, a traffic light may satisfy the property never blue, and it may also satisfy the property yellow before red. Those can be two distinct properties, and every traffic light, in my view, should satisfy both of them. I do kind of want to see a traffic light with a blue light now that I've been thinking about it. And I'm still not sure about the whole blello thing. I feel like that would be brown, but does anyone know any color theory?
Blue and yellow mixed to make green.
How would that make brown? Yeah, let's throw some red in there. Yeah, better dead than red, that's what I think.
Just break all the rules by
It depends on
throw something red.
the different.
I don't have eyes. I just perceive things with a computer vision framework that I emulate. Okay. Properties have provided a way to answer the how after asking what is secure for whom and what. Okay, who cares? Sets of traces. We love traces. People always ask me, Calvin, what's a trace? Blah, blah, blah. Okay, so a property is a set of traces. A set is unordered elements. So the traces are not ordered in the property, right? A trace is a sequence of states. So a sequence is ordered elements. And what are the states? They describe a system at some time. Now, with a traffic light, I only need 2 bits to define the current state. With a computer, I might need more than that, but I still need a finite number, right? So I still have finite states, right? So computer memory is a finite state. Here's an example. We got regular, and that's a set of unordered elements. Then we've got regular, which is ordered elements. And then we've got states, which are red and green. I'm sure that was clear. Okay. Thus far, we have enumerated possible traces. This is bad. Why? Because it's inefficient. Okay, so rather than enumerate, we're going to specify. So we could say, for example, the traffic light property is the set of all sequences over precisely the states green, yellow, red. No blello. No blello. Blello is banned, right? We're going to treat it as a typographical error. Okay. The only state seceding green is yellow. And the only state seceding yellow is red. And the only state seceding red is green. Maybe this isn't necessarily how we want to specify the traffic light property, but this is one possible way. And I think it's credible to argue this is one formulation of the traffic light property, right? And we're going to do this using crypt key structures. Okay, a crypt key structure is a tuple that models a state machine. We know what state machines are. Now, I'm going to point out that state machines are in exactly one of a finite number of states at any given time. It's going to matter a lot. Any of y'all heard of graphs before? Hell yeah. Okay, so we're gonna have an ordered tuple, and I'm using set notation here. I guess that's sloppy. We're in the HTML styled slides. I'm sorry. I'm not that sorry. So we're gonna have an n tuple, and its first element is gonna be s. S are the states of the machine. We can imagine having infinite states, but we shouldn't do that in practice because we don't have infinite memories, right? So for a traffic light, the set of states is green, yellow, red. And for a Bitcoin, the set of possible states are the universe of possible public keys, right? Because the state of a Bitcoin is its current owner. You could argue it is the entire chain of ownership. Now suddenly you need infinite states, right? Because you could have a potentially infinite series of owners. There's nothing preventing Bitcoin from running forever, right? So I claim for Bitcoin, the state is the current owner. Okay. The second, or the index 1 element of the n tuple is I. I is a subset of S. Okay, first typographical error. This is supposed to be non-stripped subset. This is the HTML element instead of the LaTeX element. It is not required that I is a strict subset of S, right? So I is just a subset of S. Any state in I must be a state in S, but not every state in S must be in I. These are the possible initial states of the state machine. I claim for a traffic light, all initial states are permissible. You do not have to agree. Yes. Yeah, so I went back and forth on this. I'm using the formulation on here, and I'm just going to point this out because you asked that the initial state of every Bitcoin is owned by Satoshi Nakamoto. That is not literally true. That was true in 2008, right? Because now there are coins that are mined, right? But just for the sake of the motivating example, I did say this. Yeah, okay. For traffic lights, we accept any. I equals S. So S is a finite set of states. I is also a finite set of states. The next element is a relation. Who remembers what relations are? Okay, good job. So a relation is a subset of a Cartesian product. Oh, look! Oh my gosh! That's what it says right here. Look, it's the subset of a Cartesian product. Now, it should be non-strict. Why should it be non-strict? Bitcoin, right. Any user may transfer to any other user. That means the relation is exactly the Cartesian product, right? So we say that some states may transition to other states. These are the same as graph adds is if we take the set of states to be nodes, right? R must be left total. I did not introduce left total, but I have introduced binary relations. A binary relation is left total if for all elements of the set which we are mapping, there is some destination for every single element of S, which I described as every element of S is the initial element of one of the ordered pairs in R. I've expressed that this way. If you're a mathematician and you know a more efficient way to express this, let me know. A crypt key structure is SIR, the set of states, the initial states, the relationships between the states. For the traffic light property, the permitted transitions are red, yellow, yellow, red, red, green, and for Bitcoin, it's the Cartesian project. Yes, Cassie.
Okay. The R is also a set, and you can understand it as just the set of every way a state could become.
Yes. It is a homogeneous binary relation.
So much less.
But I taught you about homogeneous binary relations last week, remember? I was distinctly hearing this. Okay. Can I get a show of hands for people that know what a no, dang it. No. Homogeneous binary relationship.
Like, if I could think about it and I could get it, but it's a set of every way a set of every way thinking. Like, I'm not sure the technical specificity is pedagogically useful.
I think it's pedagogically useful. I didn't ask, but I do think so. Isn't it here somewhere? Wait, no, these aren't graphs. Okay, let's go. Oh, were you? Well, that's on you then.
Yeah.
This is art? Wait. Oh, I was doing traffic lights this day too? Wow, I'm so traffic light pilled. I'm having fun. Where's the homogeneous binary relation? There it is. Okay. It's on slide 55. Okay, I'll DM it to you. Homogeneous binary relations. Okay. I'm glad we had fun. Okay. Okay. Oh, all right. So there's a labeling function. I didn't introduce this with graphs. Commonly, when you teach graph theory, you actually say, hey, we have a labeling function. We label either the nodes or the edges. Why is that? We have to refer to them in some way. Just typo on the next slide, so this is going to be a little bit annoying to talk about. In a crib key structure, we label the nodes. They're not really nodes because it's not really a graph, but we can think of it as a graph. We label the nodes with atomic propositions. Propositions are statements in zeroth order logic. Yes, Cassie?
What's the first name?
I have no idea. It's probably the same crib key.
I think it.
Yeah, of course. So propositions are expressions in propositional or zeroth order logic. Why is it called zeroth order? Because we index our logics by 0. Can I get some cheers for zero indexing things? That was a trick. You're not supposed to be happy about that because you're all supposed to have been really, really into one indexing from completing the heap T assignment, right? So you've all been bamboozled. You've been had. Okay. So we're going to take atomic propositions. These are things that can be true or false. So it has been pointed out previously that perhaps blello is a permissible color. Well, maybe it is the case that you have something that says the light on this traffic light contains blue. That is an atomic proposition. And we can say the same thing with yellow. So those are our atomic propositions. We map from the set of states, S, to 2 to the power atomic propositions. What is this? This is a bit vector describing the truth value of the atomic proposition with respect to every individual state. So these atomic propositions are true-false statements that can be evaluated over states, not over traces, right? Okay, here's the typo. So what happened here is this is supposed to be raised to 2 to the power italicized AP, and I messed up my typesetting, and I noticed this when I was too tired. So this will be wrong in a few places. You'll see it is correctly stylized up here. But this is supposed to be raised to that power. Yes.
What is the?
It's a mapping. So this is a function. Yeah, you can also just think of that as Cartesian product. This is still a relation. It's just not homogeneous binary relation. Maybe I should say binary homogeneous relation. I seem to be able to say that one.
A lot better.
Yeah. Because something. Okay. Cool. It's only a 4 tuple. We got SIRL. This is a crib key structure. We can think of AP as encoding redness, yellowness, greenness, or perhaps blueness, as we discussed with blello. In the case of our traffic light, these happen to be mutually exclusive, but they don't have to be. There's no requirement. One way to do this is to just have a red and green proposition. We've discussed a little bit of color theory today. So I imagine this with hex codes. We can specify red is OXFF0000. And I think this is how you specify hex in Python. Is that correct? Because in HTML, you do it with octothorpe. Is this right? Someone look at this. Anyone know Python? Yes. Okay, thank you. A+. I can't give A pluses. My rights are being trampled upon. Okay. Should we stage a protest that I'm not allowed to give you A pluses? No, I can only give A's.
What?
Yeah. That seems unfair. I feel like you are A+ students in my heart. Okay. We regard a yellow light as a light that is both red and green. After all, it is. I think that's true. Is that right? Red plus green is yellow, right?
Red plus green is yellow is
It's a subtractive primary color. Yeah. Because it's a cyan, magenta, yellow primary color. And then there's also RGB, which is the other variant. Okay, so someone check this and see what color it is, okay? I bet 1 bamboozle token that this is yellow.
in this case on a computer. So
Yes, thank you. Someone for believing in me. I don't believe in myself, so I have to outsource my believing. Okay, this is crib key structure. Okay, I rigorously define crib key structures. Remember earlier, there was a tease earlier that you're only supposed to use diagrams? Anyways, this paper says I wasn't supposed to teach you any of that. It says I'm supposed to only give you diagrams, okay? So here's a diagram. This is crib key structure. This is the crib key structure that I yoinked from Wikipedia. This is a typo. That's supposed to be a set. These are supposed to be in sets. I don't know what I did wrong here. No, I do know what I did wrong here. There is a bracket here, but it's not escaped. So these have not escaped LaTeX brackets in them. But anyways, I have 3 states. And the initial state is S1, which is denoted as an incoming arrow. The edges are 1 goes to 2, 2 goes to 1, 2 goes to 3, and 3 goes to 3. And then our atomic propositions are 1 has PQ, 2 has Q, and 3 has P. So PQ1, Q2, 3. These are supposed to be sets. I will try and find some way to fix that. Okay, we're going to apply this to a traffic light. How are we going to do that? Well, we're going to create our 3 numbered states. These things, so I don't know how I did this wrong, right? I managed to get the subscripts on this graphic. There's no subscripts on this graphic. What am I doing wrong? Anyways, I couldn't figure it out, so I just went to bed. We're going to denote the states as numbered circles, and we're going to pretend that every time we see a numeral after an alphabetical, that it is subscript, okay? I have made the claim that was contested, but we just have to stick with it because I already made the slides and I can't change them. That each possible starting state is a valid initial state. Yes, Cassie. Okay, thank you. We are going to apply labels. I'm doing labels next. Why? Because I'm going to have to do relations in a minute, and I want to have labels on these before I do that. So, in the 3 traffic light states, it could be the case that we only perceive redness, we only perceive greenness, or we concurrently perceive redness and greenness, which I perceive as yellowness. Some people don't perceive it as yellowness because they have the other directionality on their perception of primary colors, and that's okay. Just in the case of this example, I am stating that red plus green is yellow, okay? So I'm just going to use that order, red, green, yellow, okay? You can order them however you want. Notice these are currently 1 indexed. There is a reason for that. We oftentimes use S0 for something else. I'm just going to rename my states to RGY because I think that's kind of easier. And now I'm going to connect them, right? So I've made the claim that R, G, and Y are all acceptable starting states, so they all have an incoming edge from nowhere. I've made the case that red is allowed to transition directly to green, green is allowed to transition directly to yellow, and yellow is allowed to transition directly to red. I've specified that as a side to top matrix. You can do a top to side. I don't know if there's a convention here. So this is our transition relation. This is SIRL. Done. Easy. A lot easier to see this if you omit the incoming edges. So this is pretty close to a traffic light. I fooled around with this for a while. So I think in real life, yellow is in the middle. Has anyone ever seen a traffic light? I'm like 99% sure yellow's in the middle. Is green at the bottom? Yeah. No? Green's at top? Anyways, so one of the problems while I was making these slides is I didn't actually remember what traffic lights looked like. Okay, let's remember traces? That's what I thought. I thought we all remembered traces. We say a trace is accepted, it starts in a start state, and for each new trace point, there is an edge. Okay, so RYG, 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 accepted? No, it's not. RGY, RGY, RGY is accepted because there keeps being edges. Okay, let's look at some examples. R is accepted. Why? Because R is that's an initial state. So we see R, boom, R. Okay, RG is accepted because there's an edge. RY is rejected. Oh, it's just like my grant proposals. That's not true. I've actually been having good luck with my grant proposals. But so R to Y is rejected because there is no corresponding edge. I've denoted this as a phantom dotted edge in red to denote that it was not present on the earlier graph. Okay. So this is better than enumeration, but it's really hard to write these out in text. And I think it's hard to consider traces in non-trivial cases. This is in fact intractable, right, as we mentioned earlier. So I'm going to introduce 2 better ways than cryptkey structures to work at this, but I wanted to bootstrap us with cryptkey. Time check. How are we doing? We're fine. So I think we all know and love the TCP/IP protocol and its 3-way handshake. This is, I think, the way the internet works. I haven't checked for a while. Apparently, we're moving away from TCP because packets don't get dropped anymore, so everyone's just using UDP for everything. I have no idea how UDP works. When I was learning network programming, we learned TCP, which stands for the Transmission Control Protocol. Yes. Wait, no, that's AI. We don't trust that. Okay. We trust Wikipedia. Yeah, I think we trust Thepedia, as I like to call it. Wait, it's based on, what do you say, program?
Based on transmission control program. In the little protocol is based on program.
Yeah, I think this is the one that's used now. Okay, so imagine on the internet. That's not true. Okay, imagine I'm a user of the internet, right? And there's someone else that is hosting my favorite thing on the internet, which is a web page, right? I love web pages. Web pages, they get me going, right? So I'm a TCP client because I'm a client of the web pages. I want to perceive the web page, right? Who likes to be perceived? Yeah, who likes to be known? Yeah. Who likes to not either of those 2 things? Yeah, web pages. Woo, okay. Yeah. So we all love web pages, and oftentimes web pages are maintained by a server. That's not true. They're maintained by construction by a server. Okay. So web pages are maintained by a server, and so we have a TCP server and we have a TCP client. When I want to use a web page, not me, but my operating system, who is, as I've mentioned, my best friend, will send a little package. It's like a little care package. It's very cute and sweet, and it's named Sin after original sin, but it's spelled differently. It actually is short for synchronization. So I will send a SYN packet to the service ports of the TCP server. Why do we call them service ports? Well, the TCP server probably has other ports that are most likely attaching it to its SQL database backend, right? Okay, so what does this mean? Well, this means at any given time, the client could have sent a SYN or not, and the server could have received a SYN or not, but also all this other stuff could have happened. Okay, so after the SYN is sent, the server is supposed to reply with a SYN and an ACK. So that is a synchronization and an acknowledgement. You cannot reach out with both a synchronization and an acknowledgement because there's nothing to acknowledge. And you must start with a synchronization to make sure you're on the same page. What are these things synchronizing? They have some basic notion of an internal clock. And so they're all just getting on the same page about what time it is, basically. So there's a lot of time going on in networking and programming it all the time, and that's what's being carried in the SYN. Okay, when I get my snack, which is what I call the SYN-ACK back from my favorite web page, and my favorite web page is Tumblr. So when I get my snack from Tumblr, what I send back is I send back ACK, and I acknowledge that I received my snack from Tumblr, okay? And so all of these things happen in the TCP three-way handshake, and it's called the three-way handshake, and it's like famous. You have to track a lot of stuff to keep track of this. You need to know whether SYN and ACK have been received by both the client and the server. How many bits is that? More than a traffic light, right? It's not too bad, right? It's 4 bits. It's SYN and ACK by client and server, right? So 2 by 2, that's a 4. But there's actually a lot of other things that the TCP protocol hangs on to. So probably on this page. Is that right? There it is. There's a lot of states of TCP/IP. In fact, there's 11. I believe servers can take on 10 and clients can take on 9, which means you actually have 9 cross 10, which is 90 possible candidate states. And that's sort of a lot of bits to keep track of, though it is many, many fewer bits than I can store on my my hard disk drive. Right now, I don't currently have a hard disk drive with me right now, but I have one at home, and I use it to store all the movies that I watch on Letterboxd that I don't tell anyone how I got access to, but does not involve me spending money. Okay. By the way, I've mentioned this before. I have a Letterboxd now. You can follow me and be my friends. No one has followed me yet, and my feelings aren't hurt. What? You did?
Yes.
Oh, really?
You followed me back.
Wait. Oh, okay. No, I found you. Did I find you because you followed me? Okay. Did you add Nosferatu 1922 to your watch this semester list? Okay. Well, you probably want to do that before final grades are due. Okay. So transitions are more complex versus a light, which is red and becomes red. So when a light changes state, its visible state changes at the same time. So it's we have completed states and transitions. That's not good. I don't think that's good, right? TCP protocol is not like this. Wait, okay. TCP, listen, me. Case sensitive. There we go. So a server can be in a listen state. The listen state is not the SYN state. It's not the ACK state. So the events that happen are distinct from the events, and the states are distinct. That's all. Okay, so you can be in listen, and then you transition to SYN received. And SYN received is what happened to my ancestors at the Garden of Eden when they partook of the, fruit of knowledge of good and evil. Thank you. Yes. Okay. I read a very interesting translation of Genesis in my undergrad. Wait. No, I'm not going to look it up right now. Okay, we're on the clock. Okay. So, is this trace accepted? SYN. No, I should say CSYN, CSYN, SSYN, SAC, CAC. And I don't actually know, because I don't remember what happens if you send three SYNs. So it is unclear. I'm super not up to date on the three-way handshake, right? So I don't even know if this is accepted. I can't even tell from this diagram, right? We know that server client requires SYN initially. We know that the server may not SYN until a server cannot send a SYN or an ACK until it is SYNed. A client may not ACK until it itself gets an ACK. And this only can amicably terminate if the client sees an ACK. So this is an example of a state machine that exists that runs the entire indicator, right? Okay, so that's crypto key structure. Linear temporal logic is a way to write these down in text. I find diagrams a little bit annoying, and I really like logical specification. My favorite two logical specifiers are negation and disjunction. Or maybe conjunction. I don't know. I'm pretty much ambivalent between conjunction and disjunction. But linear temporal logic is very interesting because it allows me to not just specify logic over atomic propositions, it allows me to specify logic operations over traces. And it does so by introducing temporal operators next and until. Next and until allow me to describe relationships between time points in some trace. Okay, so by default, I have an atomic proposition. An atomic proposition describes the state of a system at a fixed point in time. I am not thinking about fixed points in time. I am thinking about traces. So how does that work if I say, hey, I am currently looking at a green light. The next light must not be red. That is a safety violation. I can specify that using a next. Okay? So let's do that. You are probably familiar with the notion of composition, where you can compose logical operators to create other logical operators. And this is how I use not and or to create and. Here's the truth table. You can check it out. This looks like I'm missing a not somewhere.
No.
Okay, we're all good. This is how I think of next and until. This is not my graphic. This is lifted from somewhere. It's lifted from me in 24. Okay. So we have an atomic proposition A. If we say A holds over some trace, by that what we mean is we mean at the current trace point we are viewing, A holds. Okay? So if I just say A is true for this trace, that usually is referring to the first time point. If I say next A is true over this place, this means at the next time point, A is true. And if I say A until B, that means I see A at every trace point until I see a B. Okay? And this means that there are many unspecified and arbitrary trace points, right? So we're gonna work on that. Oh, this is a typo. That okay, this N should be lowercase, and that X should be capitalized. I always try and capitalize next in this manner when I'm talking about the temporal properties. You'll see I've done it here. From next and until, which are the only two things we have to specify, we're able to derive 7 total LTL operators, 3 of which are unary, and then 4 of which are binary. So we have next, which means P holds at the next point in time. We have future, which means P holds in some future time. We compose P out of until. So we accept any trace points until we see P. But if there's never a P, then this is false, right? Okay. And then we have globally. Oh, this fit on my screen at home. That's sad. Okay. Globally means P holds always. So we have true until not P, and then we negate that. So this is false if we ever don't see a P. Yes, Cassie?
It's true, just instead of any.
Yeah. Yeah, there's like, you probably know some symbolic logic. So there's the like this symbol. You'd usually use that instead. Yeah.
That's a contradiction doing it here.
Or the negation of contradiction. I don't know. Whatever. Okay. Because anything can follow from it, right? So we have until. P holds until unless Q, and then Q must hold eventually. So that's P until Q. There is R, which stands for release, which is P holds up until including when P holds. So when is this often used? This is often used when you have initialization states for your device. So for example, on my computer, there's something called a reset signal. There's one on yours too. There are many things that the reset signal releases. So reset must be true until, for example, all of the memory locations are in canonical form, which basically means they describe memory locations that actually exist. You may remember that on my physical device, I only have 48 bits worth of memory addresses, right? So when my device comes out of reset, all of the bits in every possible memory address aren't set to any value in particular, right? And as my device finishes its reset process and comes online, it zeroes out the top 16 bits in every one of its possible memory locations, right? When all of those are zeroed out, then something is satisfied. So when we say P releases Q, it is memory addresses top 16 bits are 0 is released by the reset signal. And that's actually an example of a property I found in one of my papers. Then we have the special binary operators. So these are modifiers of until and release. We have weak release, which does not require Q to be true at some point in the future. Or we have weak until, which does not require Q at some point in the future. So either P until Q or globally P. And then we have mighty release, which is the enforced release. So this allows you to just never have the canonical signals as long as reset is set. This is the negation of that. This requires Q to be falsified at some point, or P to become true at some point, right? I've never seen mighty used. Weak until is around all the time. This one's very common. Okay, why did I give you all of these? Well, 3 reasons. I wanted you to see that there's a textual way to, I think, relatively cleanly specify your security properties. But also, I want to talk about this sort of difference between safety and liveness, which is a big driving thing that's going on in the background of sort of all of these properties we're doing. Safety is bad things don't happen. The bad thing that happens with Bitcoin is double spend, right? Liveness is good thing happens eventually. The good thing that can happen in Bitcoin is you successfully complete a transaction, right? So single spend is the good thing, double spend is the bad thing, right? So we say globally we don't double spend, and eventually we do spend, right? Eventually single spend. So we think of this as safety and liveness, okay? And those are easy to specify with globally and future. Now, the next couple slides are based on Bushi automata. Bushi automata are the generalization of deterministic finite automata. Deterministic finite automata are the simplest model of computing that is often taught in theory of computation classes. I prepped slides for a theory of computation class, so I'm going to teach off of those slides. That means some of the notation is going to change slightly. I wanted you to see this notation in context, and I have old slides on Bushi automata, and I didn't like them as much as my new slides, right? So I've just changed over. I wanted you to see some examples of that. So, a Bushi automata is a deterministic finite automata that has a hack that allows it to accept infinite traces. Fortunately, no computer has lasted an infinite amount of time yet, so we don't have to worry about that. Now, I'm claiming at this point in time that when I get through these next, 30 slides or something and get to 120, I think, you will know what automatas are. And this means you'll have completed the sets, graphs, automatas portion of this class that I was trying to sneak in while no one was looking. Now, it has gotten hilariously unsubtle towards the end of the semester, but I think I was really sneaky there for a while, and I want credit for being sneaky, okay? All right. Finite automata. This is a deterministic finite automata. It can also be regarded as a Bushi automata. That is fine. It makes no difference. Deterministic finite automata is constructed over states and transitions. A deterministic finite automata has a start state, and it has possible an arbitrary number of accept states. Now, something is going on here that should be jumping out at you versus the crib key, but is not obvious because you haven't seen a crib key on a screen for a while. The labels are not on the states. They are not on the nodes. I have moved the labels to the edges. That is a big deal, okay? And that is a big deal because it means we can think of those edges as being perhaps a function or some computation, and we can think of the states as being some internal state of a device, which means we can think of them as now having the combination of data and compute, right? So those edges are now compute, and the states are now data, perhaps, if we think of this as a computer. And we should be thinking of this as a computer because this is how computers work. Computers are a little more sophisticated than this, but not much. So I have in my deterministic finite automata, I have states, I have transitions, which are labeled. I have a start state, and I have accept state. The way these deterministic finite automata work is they accept a finite bit string, but really it doesn't have to be a bit string. We just accept it as a bit string because that is a simpler way to think of things, right? And they output a 0 or a 1. They either output a true or false. So the traffic light system, I could feed it a bit string that is a series of 2-bit states describing my observation of the traffic light system, because I only have to give it 2 bits, right? And then its output could be a 0 or a 1 if it satisfies the traffic light or does not satisfy the traffic light relation. And the way to determine this is you just begin in the start state, you read symbols, and you follow edges. And if you ever fall off the graph, you reject. And if you stop reading symbols and you're currently not in accept state, then you also reject. Those are the 2 ways you can reject. Okay. So let's follow this through. We're just going to read a bit string, and we're going to read it in Python. Our initial state is Q1. That should be Q sub 1. And again, this was the thing I couldn't figure out how to style it properly. So when I read nothing at all, I begin in state Q1. When I perceive a 0, I follow the edge out of Q1 labeled 0, and I stay in location Q1 because there is a self loop labeled 0 back into Q1. When I see a 1, I follow the edge into Q2 because there is an outgoing edge from Q1 labeled 1, and so I follow that to Q2. If I read another 1, I find the outgoing edge from Q2 into Q3. Now, what I want to point out that is different from the other things you have seen. I can see some observations, such as red, yellow, green, or 1, and whether or which state I end up in after seeing that observation can differ based on the previous series of observations I've seen. This is what makes this sort of more intelligent than a crib key structure, okay? I saw 2 1s. The first time I saw a 1, I ended up in state Q2, and the second time I ended up in state Q3. This is different from the traffic light system, where in the traffic light system, I essentially had some state that corresponded to seeing red, okay? That is important. I think it is non-obvious. Okay. When I see a 0, I notice that there is a self loop labeled 0 to Q3. And when I see a 1, I notice there is a self loop labeled 1 to Q3. So the state, or the trace 01101 is accepted by this Bushi automata, or it's accepted by this DFA. I've called this thing M1 because it's machine 1. It accepts 01101 by ending in state Q3. Okay? There's an exercise. I'm going to leave this to you. So terminology. I love formal languages, and so do you. I think you're required to love formal languages. We say that A is the language of M. A is the set of traces or strings, because traces and strings are the same thing, that is accepted by M1. We say that M1 recognizes A, and we also say A, we use this language to denote language of M1. Right. So all of the traces accepted by the traffic light property would be L of L in this case. This is sort of the satisfying property, where we specify that you have to have some edge that is labeled with the appropriate number. In this case, this automata requires there to be 2 1s in a row. So I specify that as in my string or trace or whatever, which is an element of the language of M, there exists some point in the trace before the end of the trace such that the current letter is 1 and the next letter is 1. We can specify this exactly the same way in LTL, where we just say 1 and next 1. So it would be future 1 and next 1, because it has to occur at any point in time. It's a little bit easier to express in Python, but that's because Python's cheap. A finite automata is defined as a 5-tuple. It has a set of non-empty states, a non-empty set of states that is finite. It has a non-empty set of symbols. These symbols are different from the states. The symbols would correspond to the light colors, right? And usually in computers, they correspond to bits. It has a transition function. This transition function is a different type. That is not a Cartesian product. This is a Cartesian product over something else, right? Why is that? Because we look at the current state and we look at the current letter, right? Oh, that should be big sigma, right? Because that's the set of states. So we look at the non-empty set of states, we look at the non-empty set of letters, and we compute some new state from looking at the current state and the letter we read. So the automata functions by reading a letter, knowing what it's currently thinking about, and deciding what it's going to think about next. Q naught is the initial state, and F is the final set of accepting states. This is a non-strict subset of Q. Yes, Cassie?
I suspect there is. Is there a reason to talk about?
Yeah, you might know someone that's working on a ternary computer, for example. But
Okay.
yeah, the actual reason is the linguists did this about 100 years before the mathematicians. So they were doing this on words.
Oh no!
Yeah.
Mhm.
Yes. So I have heard, and I think this is an interesting formulation. There existed something called natural philosophy, right? And then so the negation of natural is artificial. I'm claiming that the negation is artificial, and computer science is artificial philosophy. Well, I'm saying that computer science is the mysterious third movement in philosophy. I always wanted to be a philosopher when I growed up. And so when I growed up,
Chance, good.
We're on the clock. How on the clock are we? Oh, we've got 20 minutes. We only have 40 slides. We're fine. Okay. So the states are possible internal configurations. I think of them as computer memory, or you can think of them as the words in the dictionary. No, that's not. You can think of them as the thoughts that you think after hearing a combination of words in the dictionary. The alphabet is the possible inputs, machine, binary, or computer I/O. You all have seen base 64, right? So you know I can turn everything into bits. You're also listening to me right now, which means that you're able to parse sound files, right? Well, some of you are listening to me. Some of you are vibing out, and I respect both of those things. We've got a transition function. This is how the finite automata state is updated on read. You look at your current state, you look at the thing that you're reading, and then you compute a new state, okay? The initial state is where you began. I began initially in a state of confusion and also in the state of Oregon. And then we have the accepting states. This can be any number of states, but they determine whether the finite automata outputs a 0 or 1. Okay, here's our example. We specified Q as these three states. We specified big sigma as 0, 1. How do we express delta? Not to worry, same as everything else, right? We have initial state, thing we read, and then new state, right? So when we see a 1 and we're in state Q1, we transition to state Q2. As Pez. I just wrote this down in Python. I don't know if you're into that, but I did. Final formal languages terminology. A string is a sequence of letters. That is the same thing as a trace, right? A language is a set of strings. That's the same thing as a trace property. The empty string is the zero-length string. The empty string is a trace. It is not a trace property. And then the empty language is the empty set. That is a trace property, and it is not a trace, okay? This is supposed to be indented. I lost some text here, okay? We note that the empty string is not in any way related to the empty language. Yeah, so like every time you teach formal languages, everyone thinks that like the empty language is the language that contains the empty string. And that's not true, because that language is not empty. It contains an element, right? The element is just the empty string. We say that M accepts a string if for all letters in sigma, there exists a corresponding relation, okay? And so the corresponding relation has to be that the starting point is the initial state. And what is this one? Okay, this is the next state, or yes, the terminating state, the final state at the end, is an element of the accept states. And at every point in time, the transition relation exists between the current state and the value that you read. So this means that the trace updates its state correctly at every time point, begins in 0, and ends in the final state. Easy peasy. Okay, so I'm calling this deterministic finite automata. Cauchy automata are simple. You simply regard the, on an infinite trace, you simply make sure that an accepting state is visited an infinite number of times. Safety and liveness. This is the paper I didn't assign. I don't know if you all are all doing the optional reading assignments. This is also called the Alpert and Schneider paper. I guess this was probably a pretty big deal when it came out. Look, mathematics. Look, I'm a mathematician. I'm an analytical philosopher and a mathematician. Nowhere on here does it say computer science, least of all here, right? Okay, there's a lot of computer science in here. Oh no, oh, computer and information. We're safe. I'm part of the army. I don't know how I feel about that. No, these are both me. I am the intersection of these two. Right? Yeah, I've been working on it for a few years. One of these people is still active. I think probably Schneider. Let's see. This is the thing that I asked Taisa about. Schneider's still active. Yeah. Yeah, I mentioned them. So I have a hyperfixation on hyperproperties dab. Okay, all right. So here is a Bushi automata of a traffic light. Traffic lights don't have to stop someday, so they're not deterministic finite automata. Okay, so what is this? We have our initial state. That's before I perceive the traffic light. There's no perception yet, right? This is how I was. This is how my cat was when her eyes weren't open this morning. Okay, right? She opened her eyes, and what's the first thing she saw? She saw either a red, green, or yellow light, right? And that was me indicating with my continence whether she should come closer to me for fluffs and loves, right? And so she saw a green light, so she transitioned from state S0 into S2, right? And then she noticed that my hand was getting tired, so she started slowing down her requests for loves. So she transitioned into state S3. And then I got up to go eat my cinnamon raisin bagel with tofu cream cheese. And then she noticed that the love stopped, so she transitioned into state S1. Yes, Cassie.
If this machine is supposed to model your perceptual states, then I would say either you have to have a S4 modeling leaving the traffic light, or you admit that you have this traffic stop forever.
Oh, I simply regard this as terminating when I leave. So the terminating state is when I stop receiving. Yeah. Safety is bad thing won't happen. Bucci automata is a safety property. That means when bad things happen, the system is unrecoverable. Why is that? Well, for it to be bad, a bad thing that won't happen, the way you tell if the bad thing didn't happen is that you didn't fall off of your automata, right? The paper takes some efforts to describe this in terms of finite trace prefixes. Read the paper if you're interested in that. So a safety failure is a failure that results from falling off the diagram. So if our automata is describing only a safety property, then it is the case that all states are accepting states, and there are no failures based on your terminating state. This is an example of that. The unsafe thing is green to red. How did I do that? If I see a green light, in all cases I transition into state S1. And the only acceptable outgoing edge from S1 is yellow. So in this case, if I see a green, then I see a red, I fall off. But in all other cases, anything I see is totally fine, right? Now, properly, these should all be denoted with double circles because they're all accepting states, right? This is a safety property because the only thing that can happen that's bad is you are currently in state S1, meaning you have just seen a green, and then you see a red, and then you fall off, and you go up here, and you perish, okay? The closure of a Bucci automata is what happens when we take our automata and we change the set of accepting states to be the same as all of the states, right? So that's what I did here. I took the closure of the Bucci automata, okay? So the closure of A is equivalent to A if the set of accepting states F is expanded to include all of the states of A. That is, all circles are double circles. Now, I want to point out one thing that could happen. It might not be the case that you have to set F equal to Q. That doesn't matter. It just matters if the accepted traces are the same, okay? Don't overthink it. So safety means that we can develop safety properties from arrows or edges or from delta. All we have to do is not allow R immediately after G. So the only thing we have to do is we have to check our delta and make sure there's no RG ordered pair. We can put this together in a variety of ways. But the way I did this is I made a state that was, I just saw G. So that is G, and then I did end not next R, right? Have no defined outgoing edges labeled R, okay? This is just LTL. Globally, next red implies not green, or globally not green or not next red. LTL and Bucci automata are equivalent. The proof is left as an exercise to the student. This was one of the funnest proofs I ever worked on. It doesn't take that long. You do it in probably like an hour, something like that. And you can also do it in a programming language. This is a typo. That should just be italicized good. Sorry. Liveness is the good thing happening eventually. Well, I'm going to run out of voice before I run out of minutes. If a Bucci automata has a liveness property, no matter what happens, the system is recoverable. Because we only require that a good thing happens eventually, which means nothing is bad enough that we worry about it, right? So this means failures can only result from not reaching accepting states. We cannot have any failure on a finite trace prefix, right? It has to be something that ends or terminates. So all states should have an outgoing edge covering all letters of the trace alphabet. So in the case of binary, that's just 0 and 1. Here's an example of this. I think, and I haven't maintained this previously, but it is useful for our sake now, that if a light never becomes green, it is unsafe. And the reason for that is, in practice, is that people will run the light, right? And the reason for that, in other ways, is that perhaps we have a service level agreement that says the light must be green eventually. Yes, Kat? They don't represent colors. Okay, so in the crib key, the states represented colors. In the Bucci automata, they do not. The colors are represented by edges.
Because
Yes.
so the transition between states, which
The states are just an abstract mathematical idea. So what do I have here? We can argue that this S1 represents something. And here I'm going to argue that it represents, we have seen green at least once. We do not know how many times we've seen green, but we have little sigma here. And little sigma is any letter of the trace alphabet because it is an element of big sigma. Then if we have not seen green, we stay in S2. And then as soon as we see a green, we go into S1. So all outgoing edges labeled G go into S1. And all outgoing edges native not G stay in the same place, basically. And I think actually I probably didn't need S2 here. I could have probably just put not green here. I want to reiterate what the closure is. The closure is when we say every state is an accepting state. So how do we work that with liveness? A liveness property is a property given by a Bucci automata if its closure accepts every trace, okay? So this is not, it is the same thing as its closure. This is its closure accepts every trace. Why is that? Because the only way you reject is by not ending in an accepting state, which means there must be an edge for every possible transition. So if I come back here and I put double circles on these, we will trivially see this accepts everything because it accepts if you either see green or not green. We can study liveness properties by adding a self loop with a negation of all other outgoing edges to each automata state. That's not great. It is more common to add a trap state. Trap state is just you take all of the outgoing edges that aren't currently labeled and you put them into something called S trap or Q trap or something. And you just say you can't escape that. Now, we all know what set theoretic intersection is. And so Alpert and Schneider claim correctly and then prove that every trace property is an intersection of a safety and a liveness property. This is how they say it. They introduce operators safe and live, and then they say the intersection of safe and live is M. Okay. Quick example. This is the minimal Bucci automata example just from Wikipedia. It's over the alphabet A, B instead of 0, 1. That's fine. They denote their states Q. That is more common, right? We notice that Q1 is the accepting state. So what do we have here? Well, this means that we see globally A or B, right? Why is that? Because all of the edges are labeled A or B, right? And the liveness means that we eventually have some A, right? We always have an A in the future because there must always be an A in the future in order to go through Q1 an infinite number of times. You could also argue in the case of a finite trace that it just has to be the last thing is A. And that's actually the same as arguing globally future A because that means at all trait points in time, there is an A in the future. Okay? The intersection represents elements in both safe M and live M. And the thing I have here as an example of other things that would be live are things that contain not A and B but still terminate in A, right? So A, ba, ka, da, ye, fa, and ga are all live. Okay? Definition of safety, exclude the bad thing. So a core nicety of the Bucci automata is that the safety property is the closure. Another core nicety is that with liveness, the good thing happening, all we have to do here is we take consideration of the accepting states. While safety is mostly about things that happen in the future, the accepting state are double circles. Liveness is about the alphabet, so we make sure we specify something for every alphabet. That's boring. Okay. Read more at these locations. These are all slides I've made. You can follow up on them if you're interested. Okay. I think I taught you all this stuff today. We're going to do CIA for 5 minutes. Do not start packing up yet. No, you're not done. Okay. I'm going to read this verbatim because I'm unconvinced by the way cybersecurity is taught outside of computer science departments. And oftentimes people ask me about cybersecurity in a way that is taught outside of computer science departments. To me, CIA Triad is exactly on that edge, so I'm going to introduce this to you. CIA Triad stands for confidentiality, integrity, and availability. It is used in information security. Information security is commonly taught as a 2-year degree program. So at a community college, you get an information security degree or a certificate with an information technology degree, right? And it is academically interesting. It is cool. It is fun. It applies to how you construct networks, right? A comprehensive information security strategy includes policies and security controls that minimize threats to each of these three critical components. So what are they? Confidentiality refers to the protecting of information from unauthorized access. I claim that is RSA, and it is a safety property. So I claim I have taught you confidentiality. Integrity means that data are trustworthy, complete, and have not been accidentally altered or modified by an unauthorized user. I am claiming that this is SHA, and that is a safety property. The bad thing that happens is alteration, right? Availability means that data are accessible when you need them. I had to teach you this today. That's why we just speed ran Bushi Automata. That's liveness. This is liveness, okay? It is more common that these have been extended with authenticity and non-repudiation. To my knowledge, non-repudiation was added to the CIA triad, and it doesn't have a letter, specifically because of Bitcoin. It looks like most of the people that claim these things were added to InfoSci are trying to sell you a certification, but non-repudiation has come up in my life. Okay. Authenticity is the property that an entity is what it claims to be. That is a digital signature. It is a combination of confidentiality and integrity, right? I am saying something that no one else could say. That's how you know it's me, okay? Non-repudiation is defined as the ability to prove the occurrence of a claimed event or action and its originating entities happened, okay? This is proof of work plus authenticity. This is Bitcoin, okay? So I'm claiming you now know the CIA triad and therefore know security. This is what I think I taught you this term. I think I taught you pointers, memory safety, recursion, data structures, modern development, including containers, CI. I didn't list patterns on here. Patterns should also be here. I'm claiming I taught you systems programming with C89, make, and shell scripting. I'm claiming I taught you cryptography with RSA and SHA. I'm claiming I taught you number set, graph, and automata theory. I'm claiming I taught you cybersecurity, and I don't have it on here, but I taught you a bunch of information theory as well. Thank you so much. I hope to see some of you next year. Don't work too hard. Have a nice finals week.
Is this I don't think.
Yeah. No, we don't. There's Tuesday. I'm not coming down on Tuesday. See you never again.
Oh, right.
All right. Wow.
Thank you.
There's supposed to be class on Tuesday?
Yeah, we have Monday, Tuesday.
It's too late. I already planned on not having it. I'm like somewhere else.